that machine used a Intel 8088 CPU running at 4.77 megahertz, which resulted in the blazingly fast I/O bandwidth of 4 megabytes per second. The ISA standard, however, was created a few years later in 1984 when the PC-80, the improved PC, was created, which used the 8286 CPU. And that CPU uses a 16-bit data bus running at 8 megahertz for a total memory and I/O card bandwidth of 16 megabytes per second. There are two versions of the ISA card. The original 8-bit, which was used for the 8088 or original IBM PC. And you also have the 16-bit extended cards from the PC-80, which is technically only the ISA bus. The original one is not technically part of the ISA standard. Only the 16-bit one is actually spelled out in the standard, but commonly we call both of those card versions the ISA card. So depending on the actual CPU used, the 8088 or the 286, you can address either 1 meg or 16 meg of address range on the CPU bus and therefore also on the I/O card. Both of these CPUs support 64K of address space. One of the problems, of course, is that the ISA bus is not very fast. It was an old design from 1980, essentially. And after about 10 years, when Windows came along and other GUI-based operating systems, the I/O bandwidth was not enough to support the advanced graphics cards that started to come along. And you can here see the two different slots. This is the legacy PC, original PC slot, and this is the extended, you see the extension here, connector for the actual ISA slot, which is part of the ISA standard from 1984. So technically this is the only true ISA slot, but we refer to both as
PCI stands for Peripheral Component Interconnect. It's a mouthful. That's why we almost always call it adapter cards. You'll find both 32-bit and 64-bit versions of the PCI slot, and depending on what version of PCI happens to be running on your motherboard, you have different kinds of throughput. For instance, a 133 megabytes per second is one that you will see on a have expansion slots where we would plug in our adapter cards, and they're connecting over this 32-bit bus to the south bridge. If this was a 64-bit PCI connection, it has twice as many connections going between a much larger expansion slot and also connecting back to the south bridge. Here's a picture of the PCI slots. You can see the 32-bit PCI slot is much shorter than the 64-bit PCI slot that you'll find. Has all these little keys on it as well. Notice that each slot is very different looking, and that's because there are these little sections on the card, these notches that are on the adapter card itself, that both designate the size of the card along with what voltages are required to use that particular adapter card. You can see this card has a notch at the 3.3 volt position and the 5 volt position, and if either of those voltages are available on your motherboard, this particular card will take advantage of them. The 64-bit expansion card, much longer, you can see there's a notch in it that designates where that 64-bit happens to be. This is another adapter card that will work in both 3.3 volts and 5 volts. But if your motherboard doesn't support one of those voltages, that key space won't be available and you won't be able to push that card into the motherboard. As we became more mobile, we needed a way to take the same functionality as PCI and shrink it down for our mobile devices. So a new standard was created called Mini PCI. This had the same type of signaling, the same type of capabilities as PCI, but it put it into a very, very small form factor that worked perfectly for laptops. So we could add a Wi-Fi card, a mobile broadband card, and put it right into the laptop itself, but using a same standard as something that we were very comfortable with with the PCI format. Unfortunately, when you plug these into the laptops, they are inside under the covers of the laptop. So unlike a desktop where you could plug into an interface on a PCI adapter card, these particular adapter cards are inside of your laptop. You really don't have access to it once you install it into the system. Here's an example of what I mean by that. This is a mini PCI card. This is a Wi-Fi card that we put inside of a laptop. The cover has been removed, and it's one that gives you access. You can snap it into the slot and then put the cover right on top of it. See, there's a modem connection here. There's a slot for some additional memory if you wanted to put it into this laptop. Once you install the card, and this one happens to need an interface for an antenna, so we'll plug in the antenna connection to this. And now we've got this entire system ready to go for this Intel wireless card. We put the cover back on, and now when we start up our operating system, we have a brand new wireless card available for us. For motherboards these days, you're going to find PCI Express slots. You'll see that abbreviated as PCIe with a lowercase e. It's important to delineate the difference between that PCIX format and the newer and certainly much more common PCI Express. If you look at a new motherboard these days, they almost always are going to be primarily a PCI Express bus that you'll see on that device. You'll also see this abbreviated as PCIe with that lowercase e. This is not the PCIX for the abbreviation. PCI Express is PCIe. PCI Express also is not that traditional 32 or 64-bit wide bus. With PCI Express, we're using a serial communication to send traffic in both directions. We call these lanes. What's nice about this is that we can plug in a very slow PCI Express card and we can plug in a very high-speed PCI Express card, and they're using their own lanes to communicate. In the older PCI style, if you plugged in a slower card, the entire bus had to slow down to that speed. We don't have that problem with PCI Express. You'll see the size of these adapter connections for PCI Express as 1, 2, 4, 8, 16, or 32 full duplex lanes, and you'll see them written as X1, X2, X4, and the X here is pronounced bi. So you'll see a bi 1, a bi 4, a bi 16, and a lot of different interfaces, and they all have different sizes as well. So sometimes very easy to pick out the difference between a bi 1 interface and a bi 16 interface to be using. If we wanted to compare the different speeds between those different versions, you can see the version 1.x had 250 megabyte per second lanes in each direction. When we got to PCI Express version 2.x, it doubled the speed up to 500 megabytes per second. Although you don't see it very often, there is a standard version 3.0, and it has the capability of sending 1 gigabyte per second in either direction. And there is currently underway work for version 4.0, and it is said to increase the speed up to 2 gigabytes per second in both directions when you're working in a PCI Express environment. When you look at a motherboard that has PCI Express slots, you'll see different sizes of the slots depending on the number of lanes they're using. This motherboard also has some of the legacy PCI connectors, and here's a PCI Express by 16 slot. Here's another by 16 slot. You can see they're very long, especially when you compare them to the PCI by 1 slot. Those are relatively short, very small connections. You don't need a lot of real estate. There's only 2 lanes there that you're going to use, really 1 lane bidirectional. You've got that full duplex connection in that by 1 slot. If you were to look at the adapter cards for that, they match this. For instance, here's an adapter card that is a PCI Express by 1 adapter card, and you can see it doesn't take up a lot of room. That serial communication really allows you to very efficiently transfer information between the adapter card and the motherboard. Two is the AGP slot. This stands for Accelerated Graphics Port. We almost always call it AGP, and you'll see it written on the motherboard with the letters AGP next to the slot itself. Before we had PCI Express, we needed some way to increase the throughput for our video cards. There was a lot of gaming, a lot of high-end graphics that was required, and AGP was built just for that. So we were always able to plug in and get some additional video out of these AGP slots. But now that PCI Express is around, we have much more bandwidth available. Almost all of the new video cards that we see are using PCI Express as its slot. If you compared a PCI card with AGP, you'd see there's a lot more connectors on that AGP card. There's a lot more throughput that we needed, therefore we needed more connectors to the motherboard. Many of these cards also have these notches on them that allow you to lock that particular card into a section of the motherboard. That way, if the workstation is jostled or moved, you can be assured that that card isn't accidentally going to pop out of the slot. As AGP matured, we also got higher throughputs out of AGP. The initial versions, version 1.0, which ran at 3.3 volts, gave us what we called an AGP 1x and 2x speeds. They gave us speeds up to 522 megabytes per second. The next version of AGP, version 2.0, was a 1.5 volt version, but you can see it was a 4x, which means we were able to get 1.07 gigabytes per second out of that standard. And you can see we doubled it again with AGP 8x to 2.1 gigabytes per second. We were able to get a lot of throughput through that AGP 8x. You can also see in that 3.0 version that we had 0.8 volts as the standard on that bus. As time went on, we got very efficient with using the power on AGP, and you can see as we went through the different versions, the bus requirements itself dropped from a 3.3 volts all the way down to 0.8 volts. Just like all of the other expansion slots, AGP is very unique. You can't plug PCI into AGP and vice versa because of the format of the slot itself. And most of the time you'll see on the motherboard that it specifically says that's an AGP connection. So you can be very sure what you're plugging into and how you're connecting to that motherboard. You can see there have been a lot of different interface types through the years, and all of these buses allowed us to improve the capabilities of our computers. And if you look at your desktop, you've probably got one or two of these available so that you can add on additional capabilities to your computer. One of the key components inside of our computers is the memory. We're usually referring to memory as the random access memory, the amount of total RAM storage that you might have for that computer. But there's all kinds of different memory inside of your computer. When we're commonly talking about memory, we're usually talking about the RAM, but there may be occasions where we're talking about certain types of memory that aren't specifically associated with the RAM types that we'll discuss in this video. Another thing to keep in mind is your RAM memory is not the same as your hard drive storage or other storage device that you might have on your computer. Of course, we're using the same type of measurement system for those. We talk about our memory sticks being a 4 gig or an 8 gig memory stick, and we're talking about hard drive space also in gigabytes, so it's very common to mix those up if you aren't exactly sure what you're talking about. Memory is so important in our computers because the only time you can perform a calculation on anything is if you get that into the memory of your computer. So it's very common for us to pull files off of our hard talk about CPUs and we talk about processors inside of our computer, we often refer to static RAM. This is not read-only memory, and it's not the memory stick RAM that we would put in our computer. This is a very, very specialized type of memory that is very, very fast. It's so fast that it's exactly what we would like to use in the calculation process inside of our processors. The problem is that this very, very fast memory is very, very expensive. Otherwise, we'd be using it for everything. We can only use a small part of it because of the costs involved with this static RAM. It's also relatively large. We're looking at a CPU die right here. The static RAM are these large sections where all of this looks very similar. It's like we're looking at something from a plane, and every time you see these little fields of information, those are generally static RAM sections. Usually it's a layer 1, a layer 2, a layer 3 cache that is right there on the CPU itself. This static RAM is named static because we don't have to constantly refresh the contents of the memory for it to be available to us. As long as we have power to our computer, our static memory will keep whatever we put inside of it. Whenever we're commonly talking about the memory inside of our computer, we're almost always talking about dynamic random access memory. This is dynamic memory because we constantly have to refresh this memory to maintain the information that's inside of it. If we were not going to refresh this data, it would ultimately disappear and completely wipe out everything that was inside of this memory. That's a little different than the static memory we were just looking at, where you write it, and as long as there's constant power, it's always going to be there. That's not the case with dynamic memory. We always have to provide those updates, otherwise all of the information inside of it disappears. One type of dynamic random access memory is one called synchronous dynamic random access memory, or SDRAM. SDRAM is not static RAM. We have an S in front of that, but the S in this case stands for synchronous dynamic random access memory. It's synchronous because the memory itself is synchronized with the clock rate of the memory bus. We have to make sure those are synchronized together so that they stay in sync and we can constantly refresh and access all of the information that we need from inside of that memory. We don't see SDRAM on a lot of our modern systems. Generally, we see DDR type memory. We'll talk about that in a moment. But if you are going to acquire or replace some existing SDRAM inside of one of your computers, you'll notice that the SDRAM is labeled with the same speed as your memory clock bus. So if you have a memory clock bus of a 133 megahertz clock, you're looking for SDRAM that is a PC133. And generally you'll see that on the package that you purchase. Sometimes the memory itself, like this one, actually has listed on it PC133. That way I know the SDRAM I have here is designed for a memory clock bus rate of 133 megahertz. As our computers matured through the years, we needed to make sure that the speed of our memory was keeping up with the faster and faster processors that were created. By the time the Pentium 4 came along, we were hitting the limits of what that traditional SD-RAM was going to be able to do for us. So a third party called Rambus created a new type of memory that could go much faster. And they partnered with Intel so that you could create some motherboards that would require this Rambus dynamic random access memory. The advantage, of course, is that this memory is much faster than the older SD-RAM. One of the disadvantages, of course, is that because it was created by a third party and a number of licensing requirements were there, that it was more expensive than traditional memory that we were using in the past. And so now you had a balancing act of needing to go faster, but this Rambus memory also required additional money. Our modern memory types are based on double data rate, synchronous dynamic random access memory. This DDR SD-RAM is one that we see very, very commonly. The first one that we had come out was simply DDR-RAM, and we're associated with it. If we were to look at, for instance, a memory bus clock version of DDR memory was called DDR2. This is the double data rate 2 SD-RAM, and there were a number of enhancements associated with it. We had the ability to handle more interference. We had buffers built into this. There were drivers off chip. It was the next generation of DDR memory. It also was twice as fast. So we would take our original 100 megahertz bus clock rate. Notice that our bus clock multiplier changes to 2. All of this numbers stay the same after that. A dual rate of DDR memory is DDR3. And as you can expect, it's twice the data rate of DDR2. We even have much larger modules that we can use in our computers today. The formula, very, very similar. The only thing you're really changing is the bus clock multiplier, which means you can take your 100 megahertz memory clock rate, and once you do the equation, you come up with a peak data rate of 6,400 megabytes per second. And we can see here that we put a 3 on the end of the PC3 to designate that this is DDR3 memory. And then our peak data rate 2 in DDR3, you cannot use different types of memory on different motherboards. You can't take a DDR2 memory and use it on a motherboard that's designed for DDR3. Even if you try to do that, you'll notice that it doesn't fit onto the motherboard. So if you're moving memory around and you notice it's not quite going into the slot, there are these sections on the memory that are designed to fit right into a key that is on the memory slot itself. This ensures that when we are plugging memory in, that we're not using the wrong memory type on that motherboard. It should fit perfectly, and if it doesn't, you may want to look at the tiny little slot that is in your memory and make sure it lines up with the plastic key that is inside the memory slot on your motherboard.